Okay, we're going to work on Unit 7, Lesson 3 here, and this is all about using Kruskal's algorithm to find a minimum spanning tree. I forgot to embed this image of Kruskal's algorithm here, the steps, before I sent out the classwork file. So I sent out another file called simply Kruskal's algorithm, and that's where you can find this little screenshot. So the steps for Kruskal's algorithm, pretty simple. When you're given a network, what you want to do is you want to find the cheapest link available, okay? And you're going to pick that one, and then the next cheapest, and then the next cheapest, and then the next cheapest, until you have a connected circuit, but you cannot have any loops in it. Okay, so here we go. We will start with number 19. Here's a network. What we want to do is we want to find the minimum spanning tree using Kruskal's algorithm. So the first thing we're going to do is I'm going to point out where the vertices are. And we see there are 5 vertices, so we're just going to put our vertices in the same spot: A, B, C, D, and E. Okay, now what we're going to do is we're going to go through here, we're going to go through the original network, and we are going to find a network here that is a minimum spanning tree, and we do it this way. We find the smallest weighted edge, and that is this one, 165 from C to E. So that's going to be our first edge in our minimum spanning tree, 165. And then our next smallest one is right here, this 185. Okay, so we're going to add that in, D to A, 185. Then we're going to find the next smallest one. The next smallest one would be right here, right? It's A to C, and that is 200. Then we will find the next smallest one. Let's see here. We have next smallest one, 200, 205, but I can't really use that 205 because that would give us a cycle, right? We don't want that cycle, so we can't use that 205. Next smallest one, it looks like, is 302, but again, that gives us a cycle, so we're not going to connect E to D. Okay, we don't want that cycle. So then I come over here and I see 305. Perfect. So I'm going to put in 305. And notice once all of our edges are connected, we've created the minimum spanning tree. So that's part A is done, just creating the tree. Part B is to give the weight of the tree, and to give the weight of the tree, we just add these all up, right? Just take all of these different weights, and we're going to add them up. So we have 165, 185, 200, 305. Add those up, and we have a weight of, the weight is 855. Okay, so that's number 19. Now what we're going to do the same thing for number 21 here. Okay, so here we go. We just go through and we find the minimum spanning tree, A, B, C, D, E, and F now. So we got A, B, C, D, E, and F. All right, we come over here and we just start finding the smallest values. So I have 1.2 D to C, and then I have 1.8 E to F, and then I have, let's see, 1.8, 2.0 is E to C. So put that one in, 2.0 E to C. And then I have 2.1 is A to B. So A to B is 2.1. And then, let's see, 2.2 would give me A to C. A to C is 2.2. And there, I'm done. Notice I have all the vertices are connected. I have a minimum spanning tree. Now to find the weight of that minimum spanning tree, so that's part A. For part B, the weight of this minimum spanning tree, we just add them all up. 1.2, 1.8, 2.0, 2.1, and 2.2. Add them up in a calculator, and I get 9.3 for the weight of this minimum spanning tree. Okay. All right. Next. Now what we're going to do is we're going to find minimum spanning tree from a chart. Remember, we kind of did this before. Remember, the bottom of this chart I don't really concern myself with, right? Because this is just a repeat of the top, so I really only need half of the chart. So I'm going to ignore that stuff. I should probably, instead of highlighting it, I'll just cross it off. I'm ignoring this bottom half of the chart. Now what I need to do is I just need to set up my vertices. So I have 1, 2, 3, 4, 5, 6 different cities. So I'm just going to set up 6 different cities. 1, 2, 3, 4, 5, 6 different cities. And those cities are Atlanta and Columbus and Kansas City and Minneapolis and Pierre. And we have Tulsa. Okay, so in order to use Kruskal's algorithm from a chart, it's actually a little bit easier, because what we do is we just look in the chart and we start by finding the smallest possible number. So my smallest possible number here is 248. Okay, and that connects Tulsa and Kansas City. So then I just put in that edge, Tulsa to Kansas City, and that is 248. Okay, then I go to the next smallest. Okay, I've used the 248. Now I go to the next smallest. So it looks like next would be 394, and that is connecting Pierre and Minneapolis. 394. Now I've used that one up. So now I find the next smallest. Looks like 533 here. Atlanta and Columbus is 533. Use that one up. Now I find the next smallest. I have, I skipped one. 447. 447. Let's see, what does 447 goes from Minneapolis to Kansas City. Okay, that's good. So I can throw that in there. 447. Okay. Then the 533. Good. We're good. Next one is going to be, let's see, 656 would be Columbus to Kansas City. So Columbus to Kansas City is 656. Right, that's this one. And notice, once I have a spanning tree, I'm finished. So there is my spanning tree for this example. Okay. Now, a lot of times what you want to do is you want to name the vertices, or name the edges. And to name the edges, it's just, go through. First we did Tulsa to Kansas City. And then we did Pierre to Minneapolis. Okay, and just go through and name them. You don't really have to do that. If you draw it out for me, that'll be plenty. That's good enough. Okay, so that is creating a minimum spanning tree when you're given a chart. Now we come down here and let's take a look at number 25. So 25 is a kind of a cool problem. So here's what we have. We have a 3x4 grid that represents the networks, 3 blocks by 4 blocks. Okay, so we have 3 blocks, 1, 2, 3 by 4 blocks, 1, 2, 3, 4. So we got a 3x4 subdivision set up, right? For landscaping purposes, it's necessary to get water to each of the corners by laying down a system of pipes along the streets. The cost of laying down the pipes is $40,000 per mile. Each block is a half mile long, so each one of these is 0.5. 0.5. Okay. Find the cost for the cheapest network of pipes connecting all the corners of the subdivision. So that's going to be kind of cool. So what we want to do is we want to make sure we're connecting all of these corners. So what we have to do is we got to figure out how many corners do we have here, right? We got 1, 2, 3, 4, 5 intersections by 1, 2, 3, 4 intersections. So there's a total of 5 times 4, or 20 intersections. And the intersections are our vertices. Okay, so how many edges then? So if you remember, in order to find a minimum spanning tree, I know the most efficient is going to have the number of edges will be n minus 1, or the total number of vertices minus 1. So the total edges here is going to be the 20 vertices minus 1. So my total edges will be 19. So there will be 19 total edges. Okay. Now, each one of these edges, remember, is a half a mile. Okay, if it's $40,000 for every 1 full mile, then it's $20,000 per half mile, right? And since we need 19 of those half mile pieces, what we have here is 19 times the 20,000. Multiply that out. Minimum cost is $580,000. Okay, so that's it for Kruskal's theorem in finding minimum spanning trees.